Hello everyone, my name is Tanmay Sharma and I'm a Prime Minister's Research Fellow in the Mechanical Engineering Department of IIT Patna, and I welcome you all to this lecture or tutorial of NPTEL session on IC engines and gas turbines, where we will learn about the centrifugal compressors and its derivation and analysis, thermodynamic analysis, the work done. So how can we derive it? And using those concepts, we'll learn how to solve the problems related to centrifugal compressors. So let us move on. Now I will set my pointer to laser pointer, and here we go. So centrifugal compressors, as we all have learned till now, are very essential components of the gas turbine, wherein not only gas turbine but also other equipments, wherein these compressors are used to compress the air which is coming inside, and that compressed air is going inside the combustion chamber, wherein the fuel will be added and the combustion will happen. Then it will go inside the turbine, and there will be a pressure reduction by as the gas expands, and when the gas expands it releases its energy into the work which we require, and that work partly is done through running the compressor, and partly is used to get the net work derived from the gas turbine cycle. So you see the compressor out here is used to elevate the pressure of the air coming in, so that the at elevated pressure the enthalpy can be increased, and accordingly the whole work can be done. Means obviously in the turbine the gas needs to expand, so it cannot expand at the initial pressure stage, so it will have to be at a higher pressure, and that pressure of the air is achieved by a compressor, wherein some amount of work which is supplied to the compressor, it goes into uh, elevating that pressure. So this is how a compressor looks like. So you will see that this is a centrifugal type compressor, wherein there will be a centrifugal action, and which action that centrifugal action will be used to elevate the pressure, or to transmit the work done on to the compressor in elevating the pressure. So just a second. So what happens is that in this kind of compressor arrangement, the air will come in through the middle section that you will have. You see, if we can see, this is a single line impeller. What happens? This is a side view. So the air will come inside uh, this way. So along the longitudinal section of the shaft, the air will come inside, and the the compressor impeller. So this is the impeller. This impeller will rotate uh, along the shaft, and as it rotates, the air coming inside will be accelerated, and the kinetic energy of the air as well as the pressure energy both will rise inside the impeller that you can see out here. So this is the radial vanes out here, and this will rotate at a particular rpm, and this rotation is imparted by some work which has been done upon the compressor. As you can see, the turbine is connected to the compressor out here, so it's the same shaft, and the same shaft is rotating the compressor impellers. So this impellers are rotating. As a result, the pressure and the kinetic energy and the pressure energy both are increasing of the air, and then the air goes in through the static part, which is the diffuser. So these are the diffuser passages. These are not moving, and as it enters into the diffuser, then the kinetic energy, it reduces, because this is no longer means it is not moving, the diffuser is not moving, hence it cannot impart a kinetic energy. But as the air goes into this diffuser, the kinetic energy which is lost is used up in increasing the pressure energy. So higher pressure is increased. So it's like 50% of the pressure energy is increased in the impellers and the 50% is increased in the diffusers. And from the diffuser, the higher pressure, the pressurized air now goes to the discharge scroll, as you can see out here. So this is a this discharge scroll and the compressed air delivery. So this is also air going out of the compressed air delivery. So that's about the compressor. And you will have, this is a double-eyed impeller in which from two ways the air comes in. So here air can only come in through one of the sides, but in a double-eyed impeller, so that it has two eyes, as you can see here, and the air goes in through these eyes, and the air will go out radially through the impellers, as you can see out here. So as I was telling about the pressure rises in the impellers, so this is how it looks like. So basically the pressure will the both the pressure energy and the kinetic energy. So this is the pressure curve and the velocity curve, and the velocity curve implies the kinetic energy, as the pressure curve implies the pressure energy. These both will um these both will uh, rise in the impeller section, as you can see out here. But in the diffuser section, which is the static part, here, as no longer the work is transmitted in imparting the kinetic energy, so the velocity of the air will decrease, and this amount of decrease in velocity will be helpful to further rise the pressure, and that is what we need. A compressor should increase the pressure up to a particular level, and from P1 to P3 is the final pressure elevation that we get through a particular compressor as it goes through the both impeller and the diffuser section. So that is a particular capacity of the compressor. If we need to build in higher capacity, we will have to do multi-staging, and that way we can use uh, more than one compressor units out here in order to increase the pressure. So it will have one more impeller and again one more um, this a diffuser. Like that, we can increase the staging units and accordingly the pressure. So that's about the compressor arrangements everywhere. And since you can see the velocity rise, we'll have to use these velocities to perform uh, or to analyze the compressors. And so first we'll have a look at what velocities are associated with a compressor. So you can see here, this is basically denoting all the uh, information related to the velocities, and this is the two velocity diagrams we will have at the inlet and at the outlet. So uh, what happens is that, let us look at these velocities. So the air comes in inside radially. So the absolute, so CBL1 is the mean blade velocity at the entrance. So this is the mean blade velocity at the entrance, and CBL2 is the main blade velocity at the exit. So CBL2 is the main blade velocity out here at the exit, and these blade velocities are imparting the final velocities to uh, uh, the air coming in. So C1 is the absolute velocity at the inlet to the rotor. So C1 is the absolute velocity, and it is equal to the flow velocity. The flow velocity meaning that it is in the direction of the velocity at the direction of the flow, and there is one more velocity, the world velocity. So it is perpendicular to the direction of the flow. So the flow velocity and the world velocity will be in perpendicular always. So you will note that. So here the since the air is entering radially, the flow and the absolute velocity will be in the same direction, and it will have the same magnitude, since there is no world component out here at the entry. And see, so the world component will be later on when the air enters, so that's where the velocity of whirl at the inlet exists. CW2 is the velocity of whirl at the outlet here. So we'll talk about the outlet later. So the air comes in, and this is the blade velocity in this direction, centrifugal direction. But this was the initial, the absolute velocity. Hence, there will be a relative velocity existing, which will be in this direction, CR1. So CR1 is the relative velocity of air at the rotor. And in this direction, the air will move on, and it will finally go to the outside of the diffuser section. And there, uh, this is the alpha 1 at which the exit angle from the guide vane or inlet angle of the guide vane, and it will go to the outside, and it will have a outlet velocity triangle. And by that we mean that, so it will go with a relative velocity CR2. So CR2 is the relative velocity of air at the exit of the rotor. So here, then, yeah, the main blade velocity will be this magnitude, and the flow velocity will be in this direction. Hence, the whirl velocity, which is be the main responsible component for producing the power, will be in this direction, as you can see. And these are the associated angles with respect to that. So alpha 1 is the exit angle from the guide vane or the inlet angle of the guide vane. Beta 1 is the inlet angle to the rotor or impeller. So this is beta 1. Then outlet angle from the rotor or impeller, beta 2, and inlet angle to the diffuser, alpha 2. So these are the angles associated with this. So these velocities, from these velocities, we will have to find out what is the net work that can be imparted, net work done that is required to attain a particular velocity, or from the velocity we can see how much work will be required to by the compressor. So these velocities are important in that way. And after that, after the whole analysis part, we'll solve a few problems where we will get to know how to use those concepts and uh, thermodynamically analyze a centrifugal compressor. So moving on, so we'll have to first calculate what is the work done by the impeller, that is the Euler's work. So we'll first assume that W is the angular velocity in radian per second by which the impeller is rotating, and the work done on 1 kg of fluid will be theoretical torque into the angular velocity that we know. And what is the theoretical torque? So theoretical torque is CW2 into R2 minus CW1 into R1. So whirl velocity at the outlet into radius of that into whirl velocity of at the inlet into radius of 1. So the whirl velocity is finally contributing to the entire torque. So that's why we will um, subtract this, and that will be the net torque. And finally, this is r to omega. The omega is the angular velocity. The omega comes in and it remains constant for the inlet and the outlet. So r2 omega minus r1 omega, we can r2 omega is the blade velocity at the outlet, and r1 omega is the blade velocity at the inlet. So we will replace that with CBL2 out here, as you can see. So W becomes CW2 into CBL2 minus CW1 into CBL1 equals to, so that is the HO2 minus HO1, or that is the stagnation enthalpy, the total enthalpy of the whole air at the outlet minus total enthalpy of the air at the inlet, and that will be equal to Cp into TO2 minus TO1, which will be the stagnation temperature. And that O, wherever O comes, that is the overall or the stagnation temperature. That means if the air suddenly comes to a stop, so the air will have a particular pressure energy as well as the um, certain enthalpy and certain kinetic energy. And when it will come to a halt, the kinetic energy will be zero, and the entire energy of the air will be converted into its enthalpy. So that is the stagnation enthalpy, and that and the temperature associated with it will be the stagnation temperature. So the above equation here, this is known as the Euler's equation or Euler's work. And if the working fluid enters radially, so if the working fluid enters radially, so there will be no free whirl, or whirl meaning at the from the flow, you will see that a whirlpool, if you can imagine a whirlpool. So as the direction of the flow, the liquid rotates around the flow circumference, right? So that is the whirl. And if the fluid enters and there is no whirl in that, so the no kinetic energy is wasted on the whirl, then the work done will be Cw2 into Cbl2, and that will be the maximum work that we can derive. So our intention will be there should be no free whirl as the fluid enters into the compressor impellers. Next, using the inlet and the outlet velocity triangles, we will have CR1 square equals to CBL1 square plus C1 square minus CBL2 CW1. So how it is coming? So we need to calculate CR1. So for CR1, so that is using the hypotenuse, we can calculate. So this is alpha 1, this is not exactly 90 degrees. So for that, we'll have to use that formula. We'll have to use put alpha 1 and beta 1, and that is how it is used. So CBL1 plus C1 square minus CBL2 into CW1, and the relative velocity is CR2 square equals to CBL2 square plus C2 square minus CBL2 into CW2. So if we combine all this, so we will just derive what is CW2 and CW1, and we will put that in this equation. So we will get to know that the work done is associated with all the velocity in this way. So here the world component is not there. So world component we will substitute from this formula, and we will get CR1, C1 and CBL1 together in this formula, and we will get to know how the work, your Euler's work, is associated to all these velocity components. So this is the first term, second term and the third term. So the first term, it shows that the increase in kinetic energy of 1 kg of working fluid in the impeller, that has to be converted into pressure energy in the diffuser, and that is the first term. So the second term shows the pressure rise in the impeller due to diffusion action. So relative velocity difference. It basically means the change in the uh, uh, pressure due to the diffusion action as the relative velocity decreases from the inlet to the outlet. So as the velocity decreases, it imparts to the overall pressure rise, and that is how the second term is coming. And the third term shows the pressure rise in the impeller due to centrifugal action. So the blade velocity is right. So as the centrifugal action, the pressure will be rise as the working fluid enters at a lower diameter and comes out at a higher diameter. So for all these pressure rises, there will be some work done associated, and this is the work done. So this amount of work needs to be supplied to the centrifugal compressor. Actually, more than this, because we will also account for the friction losses and non-ideal conditions like isentropic losses. So friction loss is basically an isentropic loss because that is where the heat is generated, and we'll have to take that into account. So that's about the Euler's work, and the net power required per impeller for m kg of airflow in 1 second is given by P equals to m into Cw2 into Cbl2 divided by 1000 kilowatt. So mass into the work was in joule per kg, mass will be in kg per second, and together we will have joule per second, which is watt, and divided by 1000 we will have kilowatt. So that's the formula, that's the Euler's work. Next, we consider now a steady flow at the inlet and the outlet of the impeller, assuming that heat transfer during the flow of air through the impeller is 0. So we'll use the steady state or steady flow energy equation at the inlet and the outlet. So we will find this is the enthalpy This is the kinetic energy. This is the work. This is the enthalpy at outlet, kinetic energy at outlet, and no heat generation. But you will have to see that the work is generally in equations. You will find that the work will be in this side of the equation. So this is just basically meaning that the work is negative, and the W value is the absolute value that we will have the magnitude of the work, but the sign will be negative because the work will be uh, supplying to the system. So that is work done on the system. And you will remember in thermodynamic analysis, we take work done on the system to be negative. So that's why it comes to this side and it becomes positive here. And there's no heat transfer, so the heat generation or heat transfer will be 0 out here. Then we'll have H2 plus C2 square by 2 minus H1 plus C1 square by 2. At H2, we can actually break it into Cp into T2, H1 similarly Cp into T1, and we will take it as common and divide it by here Cp here and Cp out here. Accordingly, we'll find that is equal to work done is equal to Cp into T02, that is stagnation temperatures out here, the absolute temperatures, and from here we will go into thermodynamic analysis as such that we will take common T02 and we will have a ratio of T02 by T01. We take common T01 and that is the initial condition. That's why we take common the initial condition, and from that we will have uh, the value of T02 to be equal to T2 into P02 by P2 whole to the power gamma minus 1. Yes, we can write that because that is the uh, isentropic condition. So from an isentropic process, we can write that. Uh, and also similarly for the case of 1 here. And finally, we will cancel out the terms and uh, we will have CPT02 into P naught 2 by P naught 1 whole to the power gamma minus 1 by gamma equals to we will write this as a pressure ratio. So Rp naught is the pressure ratio based on the stagnation pressures. So these are the stagnation pressures, and finally we'll have this. So we have now written the whole Euler's work or the work done in terms of pressure ratio. So suppose we impart a certain amount of work. Now we will get to know how much will be the stagnation pressure ratio we can achieve. So we can then uh, use it along with the Euler's work and we can get how much will be the stagnation pressure ratio. That's the whole concept. So here the formula, the expressions that were used were P01 is the stagnation pressure at the inlet of the compressor, T01 is the stagnation temperature at the inlet, P02 is the stagnation pressure at the outlet, T02 is the stagnation temperature at the outlet, P1 is the static pressure at inlet, T1 is the static temperature at inlet, P2 is the static pressure at outlet, and T2 is the static temperature at outlet. So these are the expressions. Next, in most practical conditions, we will have the absolute velocity C1 and C2 are equal. In that case, we will have simple Cp W equals to Cp T2 minus T1. So you see here C1 and C2 are equal. So W will be left with H2 minus H1. So simply T2 minus T1. And CpT1, if we take T1 common, then we will again have Rp gamma minus 1 by gamma. And that is not based on the stagnation pressures. It is based on the actual pressures, actual pressure or the actual temperatures of the system. So that is minus Rp to the power gamma minus 1 by gamma minus. So that's work done, and we will equate it with C2 square, which is the absolute velocity of the fluid that is coming out, and we will relate actually that's for the uh, case out here. So in this case, we'll relate this whole case as C2 square equals to Cp T naught 1 into the stagnation pressure ratio to the power gamma minus 1 by gamma minus 1. We'll equate this and we'll find the stagnation pressure ratio equal to C2 square divided by Cp into T naught 1 plus 1 whole to the power gamma minus 1. And if C1 is equal to C2, so simply P2 by P1 will suffice, and C2 square divided by Cp T1 plus 1 whole to the power gamma by gamma minus 1. So let us note a few points related to this derivation out here till now. So the power input to the compressor depends upon the following factors: the mass flow of air through the compressor, total temperature at the inlet of the compressor, total pressure ratio of the compressor, which depends upon the square of the impeller tip velocity. So that's how we have yet got the pressure ratio. We have computed the uh, Euler's work. Now we will go into some design parameters. So for the design analysis, let us assume these things. The m is the mass of air flowing per second. V1 is the width or height of impeller at the inlet. CF1 is the flow velocity at the inlet of the impeller. V1 is the volume of 1 kg of air at the inlet. R1 is the radius of impeller at the inlet. N is the number of blades on the impeller, and T is the thickness of the plate. So we all know that the volume of air flowing per second divided by volume of 1 kg of air, that will be the mass flow or mass of air flowing per second, and that will be equal to twice by R1 V1 into CF1 divided by V1. Okay, so here R1 and V1. So V1 is the width or height of the impeller at the inlet, and V1 is the volume of 1 kg of air at the inlet. R1 is the radius of impeller at the inlet. So that is at the inlet condition, but as the air is trapped radially, so the flow velocity will be equal to the absolute velocity. So that's way we will substitute the CF1 into this equation, and finally we will have an expression for the width of the impeller at the inlet. So width of the impeller will be mass into this volume of 1 kg of air at inlet divided by twice by R1 into C1. So that's the case. And now similarly, the width of the impeller at the outlet will be equal to um, and, can be found by just replacing this everything by the suffix 2, and mass will be twice by R2 V2 into CF2 divided by V2, and we will find out for V2 out here now. So why CF2? Because that is the flow velocity, and along the direction of flow we can use the continuity equation, and that's why. But here we cannot replace CF2 by C1, so we have to use CF2. Again, the width or height of the diffuser blades at the outlet is given by the mass flow will remain constant because conservation of mass, and twice by RD into BD into CFD divided by VD, and suffix D represents the quantities at the outlet of the diffuser. So we'll just have to remember this, and at every sections we'll simply use that. So in order to get the values, we will simply find out the flow velocity at different sections, and accordingly we will be knowing the radius. We will get the value of V1, and the V1 will be V1, V2, VD will be dependent upon the temperature and pressure which is present in those sections, and we can find out that based on those values. So that's about the design of that. Now if suppose we have the thickness, we have to consider the thickness of the blades of the impeller. Then, then we will have to write so the whole radius of the impeller, but that will not have the air flowing through that. So we will have some sections utilized by the width of the blades, and in order to uh, subtract the whole, so in order to get the entire area through which the air is flowing, so we'll have to subtract the area covered by the thickness of the blades, and that is what it is doing, twice by R1 minus NT. So N is the number of blades and T is the thickness of the blades, and that is being used in all the equations out here. And accordingly, we will find we can modify the equations. Now the isentropic work done. So isentropic work done basically uh, is given by the relation eta isentropic equals to isentropic work divided by actual work equals to HO2 square, HO2 dash minus HO1 divided by HO2 minus HO1, or dependent upon the stagnation pressures as this. So this is based on the stagnation points, stagnation properties. Uh, but if the stagnation properties are not considered, then we can have the same uh, this same as what we have solved in the other gas turbine problems previously. So we can have the absolute properties as well. So in that, actually the velocity is almost considered to be equal, the inlet and the outlet, and that's why we'll have to use we use uh, the not the stagnation but the actual this enthalpies. So if the velocities are not equal, then we'll have to use the stagnation properties. So just like this, if the velocities are equal, then we'll consider the uh, actual properties, actual enthalpies, actual temperatures of the system, and that will be giving us values like this. So H0, so is here N is basically N is greater than gamma out here, and that's how the isentropic efficiency is defined. Now we'll use these concepts that we have learned so far in solving a few problems, and uh, this is the first problem, and this is a easy one. So we'll solve this problem. So we'll let us solve this problem, but first know this problem. Centrifugal compressor used as a supercharger for aero engines handles 150 kg per minute of air. Okay, the suction pressure and temperatures are 1 bar and 290 Kelvin. The suction velocity is 80 meter per second. After compression, the impeller, the conditions are 1.5 bar and 345 Kelvin and 220 meter per second. We need to calculate the isentropic efficiency, power required to drive the compressor, overall efficiency of the unit, and it may be assumed that the kinetic energy of air gained in the impeller is entirely converted into pressure in the diffuser. Okay, so we are given the mass flow through the compressor, so that is 150 kg per minute. That actually solves a lot of things. Then the suction pressure and the temperature at the inlet are given. So inlet conditions are given. So the inlet velocity is also given. After the compression, the pressure and the temperature and the velocities all are given. So I think this is a very straightforward question, and we can solve this easily. So let us take 1 minute to solve this. Mm. And after 1 minute, I will help you solve the question. Yes, let us start solving this question. So these are the things that we're given, and I think this is a pretty straightforward question. I hope that all of you has got the answers by now. So first, let us solve for the isentropic efficiency. So isentropic efficiency, since we are given the initial and the final conditions, we can simply calculate based on the temperature ratios out here. Now T2 dash is basically the isentropic through the isentropic process, whatever the temperature we get, but that may not be the actual temperature due to the efficiency part. So that is 325.26. That's the due to the pressure rise, that much temperature it would have been raised. But since we are supplying some work and there are some uh, isentropic losses, that's why the temperature of the exit gas will be higher compared to this. So that is 345 Kelvin, and we'll use this part here. So first, let us calculate the isentropic work done. So isentropic work done is Cp into T2 dash minus T1. So that is work done to raise the temperature plus, and so that is the enthalpy difference, and so this is due to the velocity difference. So C2 square minus C1 square divided by 2 minus 2 into 1000. So that in the kilowatt we are calculating, and we put in the values and we will get that the isentropic work done is 56.78 kilojoule per kg. Next, we will have to calculate the work done in the impeller. So the work done in the impeller will be Cp into T2 minus T1. So taking absolute values out here. So you will see the absolute values has now changed. So you will the 345 will be changed. Initially, due to the isentropic process, it will be lower temperature, but due to the losses, the heat will be generated, and the heat generated will rise up the temperature, and we'll have to compensate for that as well. So the work done in the impeller will be a little bit higher, and that way we'll get 76.27 kilojoule per kg. Hence, the isentropic efficiency will be isentropic work divided by the actual work, and that will be amounting to 74.45%. So that's how we calculate the isentropic efficiency. Next, we calculate the power required to drive the compressor. So that is P. Now, P is equal to mass into the work done into the in impeller. So that will be equal to 190.67 kilowatt, because we are given the mass flow rate will be 2.5 kg per second, and simply the work done we have calculated out here. We put in the values, we will get the answer directly. Now we calculate the overall efficiency of the unit. So first we need to know that as kinetic energy gained in the impeller is converted into pressure, hence the entire work done, that is Cp T3 minus T2, so um, that is equal to C2 square minus C1 square divided by 2 into 1000, and T3 is unknown. So here we will get the value of T3 equal to 365.9 Kelvin. So that's uh, at the diffuser section. So the kinetic energy of the impeller is converted into pressure. So here, from here we will get the values out at the outlet of the diffuser section, and so that is temperature to be this much. So the pressure of air leaving the diffuser P3 will be simply we will consider that as a isentropic process, and we will use the pressure ratio, the isentropic correlation, thermodynamic correlation of isentropic process, and accordingly we will plug in the values, and we will get the pressure ratio to be 1.22. We know the pressure P2, we will multiply and we will get the final pressure at the after the um, after uh, the diffuser. So that is the pressure of the air coming out of the centrifugal compressor. So that is P3. Next, after isentropic compression, the delivery of temperature from diffuser is T3 dash. So we'll have to use the this uh, T3 dash to be an isentropic process and C. So if the pressure would have been from the start to the P3, we consider this pressure to be constant, and if the process would have been isentropic, so here we did not consider isentropic process, so we included the losses. And but here, if we consider an isentropic process for the entire process 1 to 3, that is at the start of the compressor and at the end of the compressor, then we'll have T3 dash, which is the isentropic exit temperature, and that way we will get T3 dash to be 345.39 Kelvin. But you see, the temperature is higher than this because of the losses. And that way we can calculate the overall efficiency of the compressor unit. That is T3 dash minus T1 divided by T3 minus T1 and equal to 72.98%. So the overall efficiency is a little bit less, 72.98. Overall efficiency of the impeller unit was 74%. So as you go on uh, from the impeller to the diffuser, and finally you calculate the overall efficiency, you will find it will slightly decrease a little bit. So from 74 to 72%. So that was all about the first question. Let us go to the next. Now, the next question says a single inlet type centrifugal compressor handles 528 kg per minute of air. The ambient air conditions are 1 bar and 20 degrees Celsius. The compressor runs at 20,000 RPM with isentropic efficiency of 80%. The air is compressed in the compressor from 1 bar static pressure to 2 bar total pressure. Okay. The air enters the impeller eye with a velocity of 145 meter per second with no pre-whirl. So that's why the CW1 is 0. Assuming that the ratio of whirl speed to tip speed is 0.9, we need to calculate the rise in total temperature during compression if the change in kinetic energy is negligible. The tip diameter of the impeller, the power required, and the eye diameter if the hub diameter is 12 centimeter. So let us take a moment to analyze this question, and after a minute I will solve this question. Okay, then let us solve this question. So we are given these values. Mass flow rate is 528 by 6, 8.8 kg per second. Pressure is 1 bar. Temperature is 293 Kelvin. Then the rotation speed is 20,000 RPM. Isentropic efficiency is 80%. Then static, this air is compressed in the compressor from 1 bar static pressure to 4 bar total pressure, right? So P01, P02 are given. Then C1 equals to 145 meter per second, and the ratio between the whirl and the blade are 0.92. So the diameter of the uh, hub is 12 centimeter. So there is a mistake out here. So that should be 12 centimeter out here. Anyways, so this is the diagram out here. So this is the inlet of the D1 is the inlet of the whole thing, and 12 centimeter is where from where the air will enter. So at the side there is the temperature and the entropy diagram, and you see the process out here. So the process is basically 0 1 to 0 2 out here. So this is the uh, not following the isentropic path, but rather having the losses, and we will do the analysis as such that P02 is this pressure, P2 is this pressure. So from the P02 is the stagnation pressure out here, and P1 is the static pressure, and P01 is the stagnation pressure out here. So total rise in temperature during the compression if the change in kinetic energy is negligible. So for that we'll have to first calculate the stagnation temperature at the inlet to the machine. So that is T1 plus C1 square plus 2Cp, and we plug in the values, we will get 303.5 Kelvin. Then T01 means T01 by T1 because of P01 by P1 whole to the power gamma minus 1 by gamma. So you see out here T01 by T1 and equals to P01 by P1. So this part, that it is a isentropic process. So for that, we calculate P01 out here. That will be P1 into T01 by T1 to the gamma minus 1. So P1 we are given 1 bar static. So here we put in the values, we will get P01 to be 1.131 bar. So that is, so this is not 1 bar, that is P1 equals 1 bar. Then we calculate T02 divided by T01. So here you see, if the process would have been isentropic, then what would have been the case? So for that, we take the isentropic process and we calculate the temperature out here. So that is, if we plug in the values, we will get T02 dash would be 435.5 Kelvin. So this is T02 dash, and we have an isentropic efficiency of 80%. So the total isentropic rise in the total temperature is 435.5 minus 303.5. So this is the total temperature rise, and that is 132 degrees Celsius. As the total actual rise in the total temperature is 132 divided by isentropic to 165 degrees Celsius, and we'll add it to 303.5 and we'll get this temperature T02. So that's another way of doing the same thing, applying the same temperature uh, uh, based formula that we had for isentropic efficiency. So we'll add it and we'll get what is the rise in total temperature. So that is 165. So that is required. T02 is required isentropic. Total temperature rise, how much is it? So 165 degrees Celsius. So in the next case, we'll calculate the tip diameter of the impeller, that is D2. And for that, we'll have to evaluate the work consumed by the impeller. So the work that is given by Cp into delta T actual. So delta T actual is 10 Cp into 165, and that way we get 165.8 kilojoule per kg. Now the work consumed by the compressor is also given by the Euler's equation without the pre-work. So Euler's equation is CBL2 into CW2 divided by 1000, that is equal to 165.8. Now we can use the ratio CW2 divided by CBL2 equals to 0.9. So CBL2, CW2 is zero point 0.9 of CBL2, and that is being put out here. So we'll get the blade velocity out here. So the blade velocity is 429.2 meter per second, and we know the blade velocity is equal to the radius into the radius of the tip into the angular velocity, and for that we have this formula, and we know the RPM, that is 20,000 RPM, and we'll put the values and we'll find the tip diameter of the impeller to be 0.4098 meter. Now we calculate the power required P. So the power required P is M into 165.8, and M we are given. So the 165.8 is the work done consumed by the compressor entirely. So power is 1459 kilowatt. We got it straightforwardly. Now to calculate the I diameter, if the hub diameter is 12 centimeter, D1, so this part is 12 centimeter up here. So we have to calculate the I diameter. For that, we will use the continuity equation. From continuity equation, we have M equals to pi by 4 d1 square by dh square into c1 into rho 1. Now, why d1 square by dh square? So d1 minus dh, that's where the air will enter, right? So that's where the hub is used for the shaft, holding the shaft, and d1 minus d2 is where the air will enter, and that's where we'll have to consider. And so why c1? Because the flow velocity, there is no pre-word, so the flow velocity is equal to the absolute velocity. So that's why c1 into rho 1, and accordingly we'll also have to consider for the rho 1. So rho 1 is P1 by RT1, and we know the values of P1 and T1, the static pressures, and we'll get rho 1 to be 1.189 kg per meter cube. So we equate this for D1, and we get the value of D1 to be 28.2 centimeter. So that's the answer. So 28.2 centimeter, whereas the hub is 12 centimeter diameter. So we have completed the second problem. Let us go to the third problem. It states a centrifugal compressor running at 10,000 RPM delivers 660 meter cube per minute of free air. Air is compressed from 1 bar and 20 degrees Celsius to a pressure ratio of 4 with an isentropic efficiency of 82%. Blades are radial at outlet of impeller, and flow velocity of 62 meter per second may be assumed throughout constant. Outer radius of impeller is twice the inner, and the slip factor may be assumed as 0.9. The blade area coefficient may be assumed 0.9 at inlet. We need to calculate the final temperature of air, theoretical power, impeller diameters at inlet and outlet, breadth of impeller at inlet, impeller blade angle at inlet, diffuser blade angle at inlet. So let us take a moment to understand this question better, and after that I will solve this. Okay, then let us solve this problem. So We are given these values and we need to find these uh, the values. So for the first part, that is final temperature of air T2. So we'll use the same thing, T2 T dash T2 dash, that is the static part. So from that we calculate T2 dash to be 435.4 Kelvin. Now we use the isentropic uh, efficiency part, and we calculate for T2, which is higher than the T2 dash, and we will get 466.7 Kelvin. So that is the final temperature of air going out of the compressor. Next, we have a theoretical, we need to calculate the theoretical power. So the theoretical power will be mass flow rate into, first we can calculate the mass flow rate, that is PV by RT. So plug in the values, you will get 13.08 meter cube per second. Then power is the mass flow rate into the enthalpy rise, and enthalpy rise is given by H2 minus H1, that is Cp T2 minus T1. And we plug in the values, we will get the power required will be the theoretical power required will be 22.83.3 kilowatt. Then the impeller diameters at inlet and outlet D1, D2. So for radial blades, work input to the compressor is given by work done equals to phi s into CBL2 square divided by 1000. And what is phi s? So phi s is the slip factor that is assumed to be 0.9. So you can see that somehow the fluid is slipping and it is not able to uh, the whole impeller rotation is not being imparted into the um, fluid. So that is being accounted by the slip factor, and so the work done is equal to phi s into CBL2 square divided by 1000, that is equal to CPT2 minus T1. And finally T2, here is the final temperature of the air from the exit of the compressor. So we'll solve for CBL2, which we do not know, and we will find CBL2 equals to 440.4 meter per second. So that is the blade velocity at the exit of the impeller. Okay, then CBL2 is also equal to pi d2 by n by 60, and from that we'll calculate d2, and d2 is equal to 0.8411 meter. Again d1, so it is given that d1 by d2, sorry, d2 by d1 is equal to 2, and we'll use that ratio, and we'll get d1 equal to 42.6 or 06 centimeter. Next, we solve for the breadth of impeller at inlet B1. So for breadth of inlet, we'll have to consider the mass continuity, and for that we calculate the volume flow rate first. There's twice by R1, B1, CF1, KA, from where the B1 is unknown, and K is the blade area coefficient, and we are given the blade area coefficient to be 0.9. So this is blade area coefficient, that is equal to 0.9. Then V1 equals to volume flow rate divided by this value, and volume flow rate we know that is 660 meter cube per minute, and we will get 0.1492 meter by plotting all these values. So we have considered CF1 out here, and that is the flow velocity, and we need to use the flow velocities always in this kind of conditions. That is the breadth of the impellers at the inlet. Now impeller blade angle at the inlet, beta 1. So beta 1 is given by tan beta 1 equals to CF1 by CBL1, that is equal to 62 divided by 440 by 2, and equals to 0.2816. So beta 1 equals to 15.73 degree. So that is the impeller blade angle at the inlet. Next, the diffuser blade angle at the inlet, alpha 2. That is given by tan alpha 2 equals to CF2 divided by phi s into CBL2, and that will amount to alpha 2 equals to 8.9 degree. So now we'll move on to the next problem. A centrifugal blower compresses, so blower and the compressor is almost the same thing. The centrifugal blower compresses 4.8 meter cube per second of air from 1 bar to 20 uh, degrees Celsius to 1.5 bar, and the index of compression N is 1.5. The flow velocity at inlet and the outlet of the machine is the same and equal to 65 meter per second. The inlet and outlet impeller diameters are 0.32 meter and 0.62 meter respectively. The blower rotates 8,000 RPM. We need to calculate the blade angles at inlet and outlet of the impeller, the absolute angle in the tip of the impeller, the breadth of the blade at the inlet and outlet. It may be assumed that no diffuser is employed and the whole process increase takes place in the impeller and the blades have negligible thickness. So let us take a moment to understand this question, and after that I will solve this question for you. Okay then. So we are given the values, the V1 4.8 meter cube per second, T1 equals to 1 bar, T1 293 Kelvin, and which is the index of compression, that is 1.5. Then the flow velocity uh, are both equal, and that is 65 meter per second. The diameter at the inlet is 0.32 meter, diameter at the outlet is 0.62 meter, and the rotational speed is 8,000 RPM. First, we calculate the temperature at the outlet of the compressor, and that is T2 dash by T1 equals to P2 by P1 whole to the power gamma minus 1 by gamma, and from that we will get the T2 dash equals to 335.4 Kelvin. This is the isentropic the temperature at the exit of the isentropic process. The peripheral velocity at the inlet is given by CBL pi d1 n by 60, so that is 164 meter per second, and the total work done is Cp T2 dash minus T1 equals to CBL2 CW2 by 1000. So if we equate that, so we will get the world velocity component to be 164.1 meter per second. Next, we calculate the blade angles at inlet and outlet of the impeller, beta 1 and beta 2. So we needed to know the velocities, and we now know, and we will calculate the blade angles from this. So For blade angle at the inlet, CF1 divided by CBL1 equals to 65 by 134, that is beta 1 equals to 25.88 degree. Then tan beta 2, which is for the outlet, so that is CF2 divided by CBL2 minus CW2, and that will be equal to beta 2 equals to 34.2 degree at the outlet. Next, we will calculate for the absolute angle at the tip of the impeller alpha 2. So tan alpha 2 is equal to CF2 divided by CW2, and alpha 2 equals to 21.6 degrees. So you will have to use the velocity diagrams very efficiently. So you'll have to know by heart how the velocity diagram at the inlet and the outlet looks, and from that you can calculate these angles. So angle alpha 2 is equal to 21.6 degree. The breadth of the blade at the inlet and outlet, B1 and B2. So we'll have to calculate first the discharge velocity, which is dependent upon the blade. So twice by R1 B1 CF1, and we'll equate it to the how much volume of gases it goes through it. So we will equate it to 4.8 meter cube per second, and we do not know B1, so we will get to know B1 equals to 7.34 centimeter. Same we do it at the outlet as well. So we can do it the same at the outlet. Uh, so, but how done that? So, anyways, so for that we'll have to calculate the R2, and R2 we can calculate from CBL2, and we are also given the diameter, say 62, we can directly would have calculated from there. Anyways, we calculate from here as well. So V2 equals to, so we have used the gas equation. So P1 V1 by T1 into T2 by P2, and accordingly we'll get V2 equals to 3.66 meter cube per second, and for that V2, okay, so what happens is that the volume V2 at the discharge will not be same as the volume at the inlet. The mass will remain the same, but the volume at the inlet cannot be will not be same, because the pressure rises and the volume will decrease. So you see 3.66 meter cube per second, that is not same as that of the 4.8 which is at the inlet. So we can not directly use this formula at the outers. If we would have given densities and a mass flow, then we would have been able to calculate. But now, since we know the V2, we can now compute it with twice by R2, V2 and CFO. So we will have to first calculate the volume at the discharge by this formula, and after that we will equate it, and we'll get beta V2 equal to 0.0289 meter. So that leaves us at the end of the third question. Now let us move on to the next. So a centrifugal compressor delivers 16.5 kg per second of air with a total head pressure ratio of 4:1. The speed of the compressor is 15,000 rpm. The inlet total head temperature is 20 degrees Celsius, slip factor of 0.9, power input factor of 1.04, and 80% isentropic efficiency. We need to calculate the overall diameter of the impeller and the power input. So this is a very short question. So I need you guys to focus for a few minutes and to answer, to take a moment and to uh, get to the answer of this question. And after that, I will solve the question for you if you do not get it, or if you are finding some problems. Okay, then let us try to solve this question. So we are given these values: the mass fluid 16.5, and pressure ratio 4, the speed 50,000 rpm, T01 293 Kelvin, and slip factor 0.9. Then phi W is 1.04, and isentropic efficiency is 80%. So, why T01? So inlet total head temperature is 20 degrees Celsius. So that's why we have taken the stagnation temperature directly. Now the overall diameter of the impeller D. For that, we'll use the isentropic relation T02 between the stagnation pressure points, temperature and pressure points. So we know the pressure ratio, and there is the total head pressure ratio. So that's why we use that. The static pressure ratio may not be the same. You'll have to be careful what the question says. So from this, we calculate T02 dash at the exit, what is the total temperature is 435.4 Kelvin. Next, the isentropic efficiency. From that, we see what is the actual total head per temperature at the exit. So that is equal to um, okay, so we do not exactly need to calculate that. So if we need to calculate the work done, so that's why what they have done is that T02 minus T1, which is the actual temperature rise or the total head temperature rise, that is 178 Kelvin, and they have used that in the equation of work done. Phi phi s into CBL2 whole square divided by 1000 into Cp into T02 T1. So that is the total enthalpy, stagnation enthalpy difference, and that is the work imparted due to the centrifugal action in the centrifugal compressor. So that's how they have computed, and we'll be solving for CBL2 as such, and CBL2 will get us 437.2 meter per second. Next, CBL2 is also equal to pi dn by 60, and that is 437.2 meter per second. So we need to calculate the overall diameter of the impeller, and for that we just have to replace that D2 equals to 437.2 into 60 divided by pi into n, which is 15,000, and we will get D2 to be 0.55 meter. That is the first part, overall diameter of the impeller. The second part is power input, and for the power input we are given as P equals to M into Cp into T02 by minus T01, and that will amount to 2951.7 kilo. So by this, we have come to the end of the session. Let us conclude here. So here we have learned about centrifugal compressors, how it is important in gas turbine unit, and we have learned the derivation of the or the thermodynamic analysis as well as the design analysis of our centrifugal compressors. Then we have solved a few questions where we had to use the concepts of the whole thermodynamic analysis part of the centrifugal compressor. Now we are a little bit confident about the centrifugal compressors and how to attempt any questions regarding to that. So that's all for today's tutorial sessions. Hope to see you in the next week. Okay then, bye bye.